Hello students, welcome back. After a long gap, I'm starting this online class. I'm also extending your notes which I'm doing in the class itself. Now in this online class, I'm starting a different chapter. So the chapter which I'm going to start is from Unit 8, which is Atoms and Nuclei. Chapter is Chapter 26, that is Atom Origin of Spectra, or Bohr's theory of hydrogen atom. Okay, so in this chapter we are going to study about the atom, the structure of atom, and how the structure was discovered. The first topic from this chapter is alpha particle scattering experiment, known as Rutherford's atomic model. So this experiment was done by Rutherford, and the atomic model which was hence discovered is known as Rutherford's atomic model. Now, this experiment was initially accidentally discovered. It was found accidentally. In 1906, Rutherford observed that when a sharp beam of alpha particle falls on a photographic plate in a vacuum, a sharp image was formed. If, however, a thin foil of metal is placed in the path of the beam, the image becomes diffuse. This is due to the scattering of alpha particles by the atoms of the foil. Now, you might not know what an alpha particle is. So, first of all, I'll tell you what an alpha particle is. Alpha particle is actually a helium nucleus. Okay, it is a helium nucleus. Now, helium nucleus has got 2 atomic number, that means 2 proton, and it has got 2 proton plus 2 neutron. So, a helium nucleus has got 2 proton and 2 neutron. The mass number of helium nucleus is 4. The atomic number is 2. So, alpha particle is a helium nucleus having 2 proton and 2 neutron. The charge of the helium particle or alpha particle, charge of alpha particle is plus 2e. Okay, so it contains 2 proton and 2 neutron. Now, this is positively charged. Now, this happened in 1906. Now, in 1909, Geiger and Marsden, 2 scientists named as Geiger and Marsden, made a series of experiments on the scattering of alpha particle, which led to a discovery of atomic nucleus. This experimental setup was made up of gold foil, okay, very thin gold foil. Okay, the gold foil was very, very thin, but over here I'm just making it for the reference, was there, and a beam of high energy alpha particle, okay, a beam of high energy alpha particle was emitted by a radioactive element named as polonium. It was made to fall on this very thin gold foil. So a beam of alpha particle was made to fall on this gold foil. So alpha particle was made to scatter on this gold foil using the radioactive process. A radioactive element, that is polonium, was kept over here. With some reaction, alpha particle was made to emit through that polonium, and it was made to fall on this gold foil. So what happened after that? They observed that the whole arrangement was kept in vacuum so that there is no collision of alpha particle with air molecules. The particles while passing through the gold foil were deflected or scattered through a wide range of angles. Okay, now there will be atoms in the gold foil. So after coming in contact with these atoms, this alpha particle were scattered in various different angles. So there was a scintillation counter over here. This scintillation counter will count the number of alpha particle which got strike over here. Okay, it was a counter kept over here. So whenever the alpha particle touches this counter, it will be able to count the number of alpha particle. The particles scattered in various directions were counted by this. It was found that almost most of the alpha particle scattered through angles of order of 1 degree or less. So most of the alpha particle went straight. Okay, most of the alpha particle went straight or with very less deflection. But a small number of alpha particles, say one alpha particle out of 10,000 alpha particle, 1 out of 10,000 alpha particle got scattered through an angle of 90 degree. Okay, got scattered an angle of 90 degree like this. And 1 out of 10,000 got scattered at an angle of 180 degree, which is directly backward. Okay, this is what they have observed. Maximum went straight. Only 1 out of 10,000 or 20,000 went 90 degree or 180 degree. This large angle scattering of alpha particles could not be explained from prevalent ideas about atom at that time. So whatever scientists knew about atoms could not explain this few behavior of this few alpha particle. Again in 1911, Rutherford explained successfully the large angle scattering by proposing a structure of atom in the following way. So he concluded in 1911 by making few assumptions about atoms. So I'll just write it down over here. First assumption was, he said that most of the alpha particles passed almost straight way through the gold foil without being affected in the way. So if this is an alpha particle or alpha rays, okay, I'll draw the diagram over here. If it is an alpha rays, most of the alpha particle went straight without getting deviated. Okay, most of the alpha particle went straight. So from that, what he concluded was, Rutherford concluded that first one is, the atom is mostly hollow inside. Atom is mostly hollow. That is why it is not being affected by anything, it passes straight. In no case it can be solid, it was assumed by Thomson. Thomson assumed that atom is solid, entirely solid, but it is not, because alpha particles are going straight without getting deviated at any single point. So it is mostly hollow. So he just randomly assumed that atoms are kind of like this in shape, mostly hollow inside. Now, some alpha particles were deflected at small angles and their angular distributions was definite. Now, since alpha particles are positively charged, okay, alpha particles are positively charged, the part of atom deflecting them must also be positive. So whenever they are getting deflected by small angles, such as like this, when they are getting deflected by small angles, it has to be assumed that there is somewhere there is positive charge inside the atom. On that basis, he concluded that the whole of the positive charge of the atom must be concentrated in very small space. So he concluded that positive charge must be there somewhere which is very much concentrated. Not scattered, but positive charge must be somewhere inside the atom which is concentrated. Most of the part of the atom is hollow. That is the second assumption. Third one was very few of the alpha particles were scattered at an angle greater than 90 degrees from their initial path and returned back. From this, it is evident that when high speed alpha particle pass through the atom of the gold foil, then a few of them experiences a strong repulsive force so as to return back. On this basis, Rutherford assumed that a positive charge in the atom is concentrated in an extremely small space at the center of the atom. So whenever alpha ray strikes the center, because alpha ray is positive, if it strikes positive, it will repel back directly. So very few alpha particle got returned back. That means the concentration of positive charge is very small compared to the size of the atom. So this space where the positive charge is concentrated was known as nucleus. He named it as nucleus. Calculation shows that the radius of the nucleus is of size of 10 to the power minus 14 meter, and radius of atom is 10 to the power minus 10 meter. So there is a huge difference in the size of nucleus and size of atom. Thus, the radius of a nucleus is only the 10,000 parts of the radius of atom. So if you compare a big room, then a small piece of paper or small piece of chalk will give you the idea of the size of a nucleus. In the rest of the empty space of the atom around the nucleus, there are electrons only. So electrons are around the empty space. An alpha particle which happens to approach the nucleus very closely experiences a very strong repulsive force and is deflected by a very large angle. However, the nucleus is very small in size compared to the size of the atom, then the probability of alpha particle reaching the close to the nucleus is very small, and so the number of alpha particles scattered at large angles will also be very small. Now, this experiment gave important information regarding the existence of positive charge in the atom, which was not known before. The another conclusion was the alpha particle scattering experiment was regarding the scope of Coulomb's law. Now, Rutherford had assumed that when an alpha particle passes through the atoms of gold foil, the repulsive force exerted on it by the nucleus is in accordance to Coulomb's law. That is, it is inversely proportional to the square of distance of the particle from the nucleus. The particle which are on passing through the atom remains quite far from the nucleus, experiences a small repulsive force, and it goes through without any appreciable deflection. But the particle passing close to the nucleus experiences a large repulsive force and it is scattered through a large angle. So which explains that Coulomb's law holds true for atomic distances also. Coulomb's law we have studied for charges, for bigger charges, that is Q1, Q2. But it is also true for smaller charges and smaller distances such as atomic distances. And the last conclusion from this Rutherford experiment was Rutherford also acquired knowledge about the positive charge in the nuclei of an atom of different metal. So the same experiment was conducted for different foils such as gold, silver, platinum, etc. and counted the number of particles in a definite direction and found that number of was different for different metals. From this, he concluded that the magnitude of positive charge in the nuclei of different metals is different. So, different metals have different number of positive charge. That is what he concluded after repeating this experiment. So greater the number of positive charge in the nucleus, greater will be the repulsive force exerted on the alpha particle, and larger will be the angle by which alpha particle is scattered from its path. Now, on this basis, James Chadwick in 1920, another scientist named as James Chadwick, determined the positive charge in the nucleus of different metal and found that positive charge in the nucleus of a metal is Ze. Now Z, we know it is the atomic number, E is the charge of an electron. James Chadwick was the person who also discovered neutron. He said that along with the proton, there are some particles inside the nucleus which are chargeless. So he gave the idea of neutron in the same year, that is 1920, after Rutherford gave his explanation about atomic model. With this, I'll continue with another topic, that is distance of closest approach of alpha particle to the nucleus. That means how close can an alpha particle reach near the nucleus. It cannot enter the nucleus because alpha particle is positively charged. Nucleus is also positively charged, so it will repel each other. So how close it can reach the nucleus. By that we can also estimate the size of the nucleus by doing this alpha scattering of alpha particle. Now the alpha particle are emitted with kinetic energy from the radioactive source, such as radioactive element. The particle which goes straight head towards the nucleus reaches closest to the nucleus. As the alpha particle approaches the nucleus, the electrostatic repulsive force, that is, because this is positively charged, and if another positively charged, that is alpha particle, is approaching, that is twice E. The charge of alpha particle is twice E. If it is approaching the nucleus, there will be an repulsive force, which is electrostatic repulsive force. Due to that, nucleus, the kinetic energy of the particle goes on converting into electrostatic potential energy. So initially it moves with kinetic energy. When it starts reaching the nucleus, it converts into electrostatic potential energy. When whole of the kinetic energy converts into electrostatic potential energy, that is U, the alpha particle can no longer go towards the nucleus and it returns back on its same path. Thus, alpha particle is scattered through an angle of 180 degree. The positive charge on the nucleus is Ze. That on the alpha particle is twice E. This R0 is the closest approach of the alpha particle, just assuming that it can reach up to this distance near to the nucleus. Alpha particle can reach up to this R0 distance, can approach till this distance of the nucleus. Whenever it reaches this distance, kinetic energy is fully converted into potential energy and then it can no longer move inside. So directly it will be repelled back. So from here, the electrostatic potential energy, the formula for electrostatic potential energy is 1 by 4 pi epsilon naught Q1 Q2. Q1 over here is charge of the nucleus, that is Ze. Q2 over here is charge of the alpha particle, that is twice E, divided by R0. R, which is R0, that is the radius or the closest approach. This becomes 1 by 4 pi epsilon naught twice Ze square divided by R0. Now initially, alpha particle moves with the kinetic energy. This initially is the kinetic energy, that is K. So this is 1 by 4 pi epsilon naught twice Ze square divided by R0. Or from the same equation, if you cross multiply this, we get R0 is equals to 1 by 4 pi epsilon naught twice ZE square divided by K. This is the expression of distance of closest approach of the alpha particle to this nucleus. This is how close an alpha particle can reach near the nucleus. And we can also have an idea of the radius or the size of the nucleus. So the value of this R naught depends upon the initial kinetic energy of the alpha particle. Okay, this can be calculated. The formula for kinetic energy only is K is equals to half mv square. So using this you can find K, and after finding K you can find the radius of the nucleus. So with all these calculations and assumptions, Rutherford gave the model of an atom. Rutherford presented a model of an atom called the Rutherford's atomic model. In this model, the mass of the atom, leaving the mass of the electron, was concentrated at the center. Okay, which is the positive charge was concentrated at the center of the atom in a nucleus of radius. So atom has a nucleus which has got radius of 10 to the power minus 15 meter. Around the nucleus are the electron distributed in a hollow sphere of radius, in a hollow sphere which has got a radius of 10 to the power minus 10 meter. He told that the electrons are distributed randomly. Okay, this is what Rutherford assumed. Rutherford assumed that the electrons in the atoms are not stationary. So these electrons are not stationary but are constantly moving. They are revolving around the nucleus in an orbit, and the necessary centripetal force is provided by the electrostatic force of attraction between electron and the nucleus. That is what Rutherford has assumed. But this model has got two major drawbacks. Okay, this is very important to know the major drawbacks of Rutherford's atomic model. First one was regarding stability. Regarding stability of atom. So electrons revolving around the nucleus have centripetal acceleration. When an electrons are revolving, so this electrons will be accelerated. This E will be accelerated. According to thermodynamics, accelerated charged particles radiate energy. We have studied in electromagnetism or electromagnetic waves. Electromagnetic waves are accelerated charged particles. So whenever a charged particle are moving, it gets accelerated, and when it gets accelerated, it emits electromagnetic waves. Hence, electromagnetic waves should be continuously radiated by revolving electrons. So when they move, they radiate electromagnetic waves. It should radiate waves. Due to this, if it continuously radiates wave, there will be a loss of electrons. Loss of energy in the electrons. Not of electrons, but loss of energy in the electrons. The radii of their orbit should be continuously decreasing. So whenever an electron is revolving around a nucleus, the energy keeps on decreasing. So the radii of this will keep on decreasing, and ultimately this electron should fall into the nucleus. This is what happens when the electron keeps on revolving around this nucleus. So this atom cannot remain stable. So this is a problem regarding the stability of the atom. This was the first drawback. Now second one was regarding explanation of line spectrum. It was regarding the explanation of line spectrum. In Rutherford's model, due to continuously changing radii of the circular orbits of electron, that means when it keeps on changing the radii or the radius, the frequency of revolution of the electron must also be changing. So the frequency lambda keeps on changing with the radius. As a result, the electron will radiate electromagnetic waves of all frequency. So this will, if frequency keeps on changing, the frequency should change continuously. That is, the change of frequency should be continuous in nature. But experimentally, the atomic spectra or the frequency are not continuous. They are sharp lines of particular frequency. They are not continuous. So an atom should radiate waves of some definite frequencies only and not of all frequency. Thus, Rutherford model was unable to explain the line spectrum also. So it was unable to explain the emission of frequency, which was not continuous. So this difficulties was overcome by Niels Bohr with the help of quantum theory, which we are going to study in the next section. So these are the two drawbacks of Rutherford model of atom. Now, even if Rutherford's model of atom has got few drawbacks, he could explain the concept of atomic number, mass number, and neutron number. This has been explained properly. So now we know that mass of an atom is concentrated at the nucleus. And nucleus is made up of neutron and proton, and electron revolves around it. So the entire positive charge is in the nucleus. We shall later learn that nucleus has, till now it was actually not known that nucleus was proton and neutron, which was learned later on. The nuclear particles, proton and neutron plus proton, are combinedly known as nucleons. The protons give positive charge to the this gives the positive charge, and neutrons are neutral, which doesn't have any charge. The total number of protons and neutrons is equal to the integral value of atomic mass and is also known as atomic mass number. Atomic mass number is denoted by A, which is number of neutron plus number of proton. The place of an element in the periodic table is decided by its atomic number only, that is Z. Atomic number, which is the number of proton. And what we know is number of proton is also equals to number of electron. So when number of proton and number of electron are equal, an atom becomes electrically neutral. So I hope you know all these facts. Whenever we represent an element, we write the symbol, the atomic number at the bottom, and mass number over here. So this is how we represent an element. Few examples are given in the book. You can go through that also. So now in the next class, I will discuss about Bohr's atomic model and Bohr's theory of hydrogen-like atom. So this much for today. Thank you.